All right, I think it's time. So, Maya, the floor is yours.
Awesome. So my plan for today is first half more expository, second half talk about a project that I did last year. So I guess the first half is going to be about Turán numbers graphs, and I'll introduce this, I'll prove the Erdős-Stone theorem if you're familiar with that, and just try to generally introduce some of the preliminaries in this area. I realize this might be familiar for some of you and unfamiliar for some of you. So
Let's do this. How many people know the Erdős-Stone theorem?
The theorem or the proof?
The theorem.
What's the statement?
No, okay, so you get worried. I just want okay, you see what I told you.
yeah. I didn't believe Avi when he said that probably all of this would be new. The theorem is that the Turán number of a graph is determined by its chromatic number.
Okay, now I know.
Okay. So let's start at the very beginning. The Turán number of a graph and this is also called the extremal number, so it's written x of nf. And the forbidden graph f is always going to be f for forbidden, is going to measure the maximum number of edges you can have in an f-free graph. And this is parameterized on the number of vertices. So the natural question is, what is this quantity? What is it asymptotically? So the first few results I'll show, we can actually determine what this quantity is exactly. But in general, as we'll see, it's not actually reasonable to try to figure out what this graph is, what the extremal graph is exactly.
But this is induced embedding, right?
No.
No.
Just some.
Yeah. Yeah, I guess not induced free. Or not necessarily induced. Yeah. Is proper subgraph the way to say it?
Subgraph.
Subgraph. Yeah. Although I guess our first application will be cliques, and for that it's the same.
Okay.
So it's not, oftentimes we can't figure out what this quantity is precisely because what we think the extremal example is, you can actually toss in a few more edges and do something weird. So sometimes it's more natural to think of the Turán density, which is the limit of the density of this graph as n goes to infinity. And this is going to be denoted by pi f. So if you're seeing this for the first time, you're probably thinking, how do I even know that that limit exists? And I think you can take it on faith that it exists. I'll leave it as an exercise. The rough idea is you say, well, suppose I have a graph on n plus 1 vertices. That's f-free. Well, then each of its n vertex subgraphs are also going to be f-free. So the density of each of those n vertex subgraphs is going to be at most xnf. And that shows that this density keeps going down. Okay, I guess I didn't leave it as an exercise. And I should say in the second half of this talk, we'll do all of this for hypergraphs. So this n choose 2 becomes n choose whatever the uniformity is. So the first theorem in this area was Turán's theorem. Which determined what this Turán number is exactly for cliques. So one way I can write it is that the extremal number of ks plus 1 is something like 1 minus 1 over s plus some little of one term, or minus the little of one term times n choose 2. And that's actually not what he proved. He proved something stronger. He showed that the unique extremal construction is a balanced bipartite graph or blow up of chaos. So I guess throughout this talk, we'll see two different types of results. We'll see numerical results and we'll see what are called structural results. So I guess it's worth mentioning that usually we phrase the theorems as numerical results, but the results we actually care about are instrumental results. So somehow what this theorem is really saying is that the extremal number is the density of a blowup of chaos. And you can compute what this number is exactly. You can just get rid of the little o of one term if n is divisible by s, and otherwise it's a lower order factor that I don't want to compute.
And you should say what the block is just.
Oh, yeah. So, for example, if you have s equal to 3, then you'll take 3 chunks of vertices and you'll put complete bipartite graphs between them. So you start with a triangle and then replace each vertex with an independent set. And balanced means the 3 parts have size as close to n over 3 as possible while still being integers. So any other questions about?
And there's no edges in the like chunk.
Correct. Yeah, because if I had even one edge within this part, then I'd be able to build a K4 by taking one vertex here, and that edge.
In general, block, you would place the vertex with a large independent.
So I guess I want to sketch 2 proofs of this. One that I think is possibly my favorite proof, but not the most enlightening for getting a structural result, and one that I think is a little bit more boring, but does give you the structural result a little bit more easily. So the first proof is, I think, in the probabilistic method. I think, yeah.
One more question. So, in what sense it's unique?
So if you have a graph with this many edges, then that graph, and it's ks plus 1 free, then that graph must be a balanced blowup of ks.
With some explicit small of 1.
Yes, sorry. I should say equals the number of edges in balanced blowup. Okay. Yeah, good question.
And it's stable in the sense that it
Yes.
grows.
So the third type of result that you can prove, which is generally much harder than numerical and structural, is stability. So a stability result says something like, let me just put it on this board for now. If G has something like the Turán density minus a little bit edges, then G is almost an extremal example.
And is F free, right?
Sorry?
And is F free.
Yes. So I should have written for every epsilon there exists a delta such that then G is delta close to the structural, optimal delta close structurally to the extremal example. for example, if the extremal graph were bipartite, as in the case where F is a triangle, then a stability result would say something like G differs from a bipartite graph, or even from a complete bipartite graph, on only a delta fraction of edges. So this is generally much harder to show than I think in terms of hardness, numerical is the easiest, then structural, and then stability. So it's usually way harder to show, but sometimes you need it.
But it's always, it may be always true.
Yeah, I think
You don't have a counterexample.
we know that it's true for graphs. So we do have stability for Turán's theorem and also for the more general theorem. I think for hypergraphs, I'll tell you more about hypergraphs in the second half. We'll come back to that. But sometimes the extremal example is not unique. But yeah, I guess we'll talk a little bit more about stability later, but just know that stability exists for this theorem. And if you want it to work really hard, I'll leave it as a very hard exercise to turn these proofs into stability results. I don't want to do it. So the first proof I want to tell you is probabilistic. So suppose G is ks plus 1 free. What I'm going to do is I'm going to randomly permute the vertices of G. And what I'm going to do is I'm going to look at so here's V1, V2. I'm going to look at the vertices that are connected to all of their predecessors. So maybe V2 is connected to V1. I don't know, maybe we have edges that look like this. So in this example, V1 is connected to all of its predecessors because it doesn't have any. V2 is connected to all of its predecessors. V3 is not because it's not connected to V2. I think I drew V4 so that it is and V5 isn't. And I'm going to let U be the set of vertices that are connected to all their predecessors, that are connected to all their predecessors.
That's a clique.
So that's a clique. Now we've said G is ks plus 1 free, so that tells me that the size of U is at most S, deterministically, because it's a clique. But now I can instead compute the size of U by linearity of expectations. I can just sum over each vertex V and compute the probability that V is mu. And if you ask, what is the probability that V is in U? You're asking, what is the probability that among V and its non-neighbors, V comes first? Well, the set of V and its non-neighbors has size n minus degree V. And so there's a 1 in this quantity probability that V comes before all of its non-neighbors in the ordering. And by convexity, this is at least n times 1 over n minus the average degree of G. So convexity just helps us in this direction. So now if you rearrange, you get that. So just taking the inverse of both sides, 1 over the size of U is at most 1 and you get that the average degree of G is at most 1 minus 1 over S. So I went through that kind of fast, but the main idea is somehow we magically get this random ordering, and it so happens that, I guess deterministically, we find a clique, probabilistically we compute the size of that clique. And I will also say this gives one minus one over s without the little o of one. If you wanted to really be pedantic and get the right number out here, you could realize that each of these quantities has to be an integer. And so the best you can possibly get if each of those quantities is an integer gives you a slightly stronger thing out here. So you can get the exact numerical bound, but it's a little bit, and you can extract the structural result from this, but it's a little bit harder to see why the structural result holds. So the second proof I want to show.
It also shows that in a
Yeah.
random unit, like in a random ordering, you get this set of the right size.
Yeah.
Which is a bit surprising given is it like you have to pick at random the first numbers?
Yeah,
should be
so if you
in the
look at
construction, I mean.
the extremal example, let's say we're looking at K5 free, and I randomly permute my vertices. Maybe the first vertex is in this set, the second vertex is in this set, the third vertex is also in this set, the fourth vertex is here, fifth is here, sixth is here, or something like this. Then your set U is going to be equal to the first vertex you pick from this part, the first vertex you pick from this part, first from here and first from here. So actually what you said is one way you could extract what the structural construction should be. Because it tells you that if the size of U is sometimes strictly less than S, you get something stronger. And this is the sort of argument you do if you want to get a stability result. You just really drill into the argument and you see, okay, where do we lose if we don't look exactly like the extremal example? How much do we lose? And then you suffer and do a lot of computations.
Here it's easy because it's easy to guess the extremal example.
Yeah.
In general, can you see the extremal example here without? And
The proof to you are just done, so we'll see what happens for general graphs. Clicks are easy, yeah.
Yeah, I guess maybe generally when you're trying to prove these theorems, it helps to know what the extremal construction is in advance. I think that very much guides what the proof techniques should be, because otherwise you don't know what things should be, what inequalities would be tight and what inequalities would not be tight. So the second proof I have is, I'll just sketch it, is a proof by induction. So what I'm going to do is I'm going to pick the vertex that has the maximum degree.
Can I just
Yeah.
about one? So it's like another way I could think about this is like in some sense your proof is like an algorithm that like you hand me an arbitrary graph, either it will find a large clique or it will I don't know.
Well, it's a randomized algorithm.
Right, yeah, it's a randomized algorithm. Like you could run, if I hand you a graph G, you could run this, right?
Yeah, so it's a randomized algorithm that will always hand you a clique, but the size of that clique is not guaranteed to be big.
Right.
And in expectation, it's big.
Yeah. So either it will hand you a large clique or it will give you.
Oh, if the number of edges is larger than the Turán bound, then it will, with high probability, give you a large clique. Is that right?
I think it will with constant probability.
Yeah, it's just expectation.
Yeah.
I see.
Or I guess you can run it and either it'll hand you a large clique or I guess you'll find some vertex with high degree or something like that. Is that right?
Let's say you're granted that there are more edges than the Turán bound. Then it will be a good growth.
Okay.
Yeah, okay. Yeah, I've never thought about it that way. I think this one might be a better algorithm for finding a clique. So pick a vertex with maximum degree. And I'm, once again, same setup, G is KS plus 1 free. And I'm going to look at its neighborhood. So now I know that if I look at V and I look at its neighborhood, what happens within A is KS free. So if I'm inducting on S,
Right.
No,
Yes,
KS.
Yeah, very good, yeah.
yes, because if I find a copy of KS in here, I add V and I get a copy of KS plus 1. So if I'm inducting on S, then what I realize is that the neighborhood of V must be KS free. And then every remaining edge must be in the neighborhood of some vertex not in A, of which we know if this is W, the degree of W is at most the degree of V. So I've drawn the part sizes poorly here, but you should think of the yellow set as being one of those 4 parts and the white set as being the union of the other 3 parts. So in this example, we see that the number of edges in G is at most the number of edges in A. I'm going to write G induced A for the subgraph of G on A. Plus n minus A times the degree of V. And well, we know the degree of V is A, so I'm just going to put that in there. So this counts the edges within A, this counts all of the yellow edges. And I won't do the computation, but if you look at the Turán graph, you realize that this thing is going to be, that this inequality is tight for the Turán graph. That this thing is going to be at most the number of edges on a blow up of KS minus 1 on A vertices plus n minus A, say. And the last step is you have to convince yourself that this is in fact the number of edges in the best possible blow up of KS. Because you pick A vertices for the union of S minus 1 parts, and then this is what you get. So that's how you can reinterpret this quantity. So this result also makes it very easy to see what the extremal structure should be, because you only don't double count yellow. You would double count yellow edges unless this yellow set was independent. So that already gives you tightness. So let me move on to proving the more general result, but are there any questions about this first?
So this gives you the exact bound.
It does give you the exact bound. Yeah, so this gives you both the exact numerical result and the structural result.
Again, how do you show that the yellow part is independent again?
You don't, I think what I'm saying is that in the extremal example, if all of these inequalities were tight, then the yellow part would be independent.
Right.
And the reason for that is because this quantity is you take every vertex W and you look at its degree.
Yeah.
And if you have a yellow edge, if you have an edge within the yellow part, it gets double counted.
Oh, okay.
Is there a way to get stability out of this argument?
Assuredly. I think generally, probably if I was doing stability, this is the argument that I would use. I think, yes, but doing stability arguments is a lot of work. Having had to do them before. So maybe that will be my refrain throughout this talk whenever someone asks me about stability. You can probably do it, but it's a lot of work. And you don't want to, or at least I don't want to. So the more general result that I want to build up to is a theorem of Erdős-Stone, which says that the Turán number of any graph, well, if f has chromatic number equals s plus 1, then its Turán density is also 1 minus 1 over s. And the lower bound is from the same construction. Because any blowup of Ks will contain f. So that tells me that I have an f-free graph because f has chromatic number s plus 1, and blowups of Ks are s colorable. So that tells me that I have this lower bound because 1 minus 1 over s is the density of a blowup of Ks. So the challenge is really doing the upper bound. And let me erase. What is this?
I think if you're above this threshold, you'll see any graph with this chromatic number.
Yes.
N is big enough.
Yes.
You know how big N has to be?
Not offhand. Yeah, I think maybe people do. I don't know offhand. I think a lot of these problems have been studied in great depth. So for example, for cycles, we know exactly what the Turán number is. I believe for the entire spectrum of N, we know it stabilizes at some point into just being a complete bipartite graph. But below that, I believe we know exactly what the constructions are.
You have good algorithms for like finding a copy of f in a graph with too many.
Hold that thought until we talk about supersaturation, and then
Okay.
maybe you can tell me if it turns into an algorithm. So I guess one thing I should mention is if we look at this theorem, it says something if the chromatic number is at least 3. But if the chromatic number is 2, then what this says is that the Turán density is 0. And there's a whole rich study of saying the Turán density is 0 is the same thing as saying that the extremal number is little o of n squared. And there's a whole rich study of asking what is the exponent actually. We don't even know that it's necessarily a polynomial. There might be lower order terms. But I won't talk about that today, other than saying, let's start proving Erdős-Stone by proving it for bipartite graphs. So this theorem is called the KST theorem, both because it was proven by Kovács, Sós, and Turán, and because it deals with the complete bipartite graph KST. So the theorem is that the extremal number of KST is big O of n to the 2 minus 1 over s. And the big O is n goes to infinity. I think throughout you should think of graphs being fixed and going to infinity.
Some people call this a Zarankiewicz problem.
Yeah. For bipartite graphs, determining the extremal number is the Zarankiewicz problem.
So
Not proving this?
Yes, it starts by proving it for the case chromatic number is 2.
Yeah, so let me remark that this,
For the exponent is 2 minus 1 over s, right? Are you assuming which one s and t, which one is larger?
I can assume that S is less than or equal to T.
Yeah, S is not there, it's not the same.
But if you swapped them, you would get the other bound, it would just be less good.
Yeah, I'm just pointing out it's not the same S over there, it's just
Oh, yes, it's a different S.
different.
Sorry.
Just you don't want to see a bipartite graph S by T complete.
Yeah, sorry, I did not realize I was using the letter S.
This is one.
Yes. So it implies Erdős-Stone. You know what, let's just change all of these S's to K's.
Historically, I mean, this is
Uh-huh.
what was proven before, first.
Well, it worked. Think about it.
I didn't,
Erdős-Stone may have been earlier, although, yeah, I think that's really late. But anyway, very early, maybe 50s, last century.
Anyways, play history.
Right.
yeah, I think Erdős-Stone was earlier, but I don't remember offhand. They were all in the like,
Okay, so they had a different
50s,
argument
60s.
for this.
yeah, so I think the argument I'm going to show.
Yeah.
The argument I'm going to show is not the original Erdős-Stone
Okay.
proof, but it's 10 years, 20 years later, also due to Erdős.
This theorem is this type.
Yeah.
This one?
Yeah.
So it's tight for T at least S minus 1 factorial plus 1. We might know something a little bit better now, but still on that same order. And it's conjectured to be correct for S, at least T, or sorry, T at least S. So this is still, if you could prove that this was tight, that would be extremely cool. But unfortunately, it's only known to be tight for very large T.
I mean, when S equals 2 and T equals 2, this is also tight.
Yeah.
Right, sorry. It's also known, yeah, it's also tight for
So for small values,
Also three.
S equals 2 and
it's in small values.
something like this, I think.
Yeah.
Yeah. Or I guess this just means S equals 3. Yeah. So the first open case is S equals 4. Thank you. So the proof idea is basically,
First condition.
sorry?
I think this is included in what you wrote, S minus 1 factorial plus 1.
Oh, I don't think it's true for, if T equals 3, or sorry, if S equals 3, then
Yeah, okay,
Oh.
fine.
maybe I did, yeah. This one, I might have something wrong, but that's certainly the style of the lower bound. So the proof idea for this is we're going to count we're going to count copies of K1S, so the bipartite graph with one vertex on one side and S vertices on the other side. And so one way we can count these is I just pick the left vertex and then I look at the number of neighbors and I take that to S. And by convexity, this is at least n times the average degree choose S. And on the other side, I know that each set of S vertices if I take a set of S vertices and I look at their common neighbors. This is a set of size at most t minus 1. So what that means is that the number of is I sum over each set U of size S. The size of the common neighborhood of U. I don't quite know how to notate it, but it's the size of this set. And I can just upper bound that as there's n choose S choices of U and t minus 1 choices, or this value is at most t minus 1. And I'm just going to do these asymptotically, so this is roughly n to the S, and this is roughly n times e over n to the S. So if we combine these two bounds, what we get is that E is the number of edges.
Oh, okay.
Sorry, maybe I should put that on the definition slide.
Yeah, no, it's fine. Yeah.
Okay. Yeah, sorry, I should have said that several proofs ago.
Yeah, no, it's fine.
So n times E of G over n to the S is asymptotically less than or equal to n to the S. And if you rearrange, you get that E of G to the S is at most n to the 2s minus 1. Or the number of edges is asymptotically less than n to the 2 minus whatever else. And I think in the interest of time, I will say, but will not prove, that you can do a similar thing for bipartite hypergraphs. So you can induct and use this to show, well, if I have a 3 uniform bipartite graph, I pick
What is it? Hypergraph to be bipartite.
tripartite, thank you. Let me actually just write this out a little bit. So if I have, I'm going to denote by, so whenever I write a hypergraph, R is going to tell you what the uniformity is. So what this guy is it has R parts. Each has S vertices. So this is an example where R equals 3. And then my edges are going to be all R tuples that take one part in each set. So this is an R uniform R-partite hypergraph. And the result is that this thing also has extremal number a little bit less than n to the R. So every time you run the induction step, you lose a 1 over S factor in this error term. So I won't give you the whole proof, but the rough idea is you look at S vertices. Yeah.
Small question, sorry.
Yeah.
If these were different S's, then it will be dominated by the smallest one, similar to the above.
So if it was S1 through SR, then this would be S1 times S2 all the way to SR minus 1. Yeah, I think for today, all I care about is that it's little o of n to the R. So the rough idea is that I'm going to pick S vertices. or S1 if I were using different sizes. And I'm going to look at an R-1 uniform hypergraph. By taking for these S vertices, whenever I have an edge like that, and an edge like that, and an edge like that, then I'm going to put this into my R-1 uniform hypergraph. So if my S vertices are called V1 through Vs, I'll call my R-1 uniform hypergraph G prime. Then I want to take every R-1 tuple that forms an edge with V1 and forms an edge with V2 and forms an edge with V3. So in this example, we started with a 3 uniform hypergraph, and then this 2 uniform yellow edge would be in G prime. So I'm not going to do out the computation, but the rough idea is that G prime is K R-1 S free. Because if G prime had one of these structures, then G would have the structure 1 uniformity up. And you essentially induct and you count the number. You induct and you count the number of edges in G prime if you picked a random collection of S vertices, and you do one of these same convexity tricks that we've been doing a lot of. So I think in the interest of time, I'm not going to say too much more about this proof, but I'm happy to take questions since this is a very useful result. Yeah. Sorry?
Like, where, like, who this is this part of KST or?
I don't think so. No, it's not.
Yeah, I
Is this a
actually
folklore
didn't.
argument?
When I was prepping this, I didn't find a citation to it.
Oh, okay, so just.
Yeah, I can check.
Okay.
Oh, is this bond tight?
I think it's also known to be tight for some regimes, but it's not known to be tight for SSSSS. Or sorry, it's known to be tight for some regimes of S1 through SR if they were all distinct, but it's not known to be tight for all S.
I never saw construct. Although the construction there is quite interesting. These are called norm graphs, and they are formed explicitly with S factorial uses some not trivial algebra axioms.
Yeah, it's a very. I remember seeing this construction once, and it was very nice and very clever. But I think in the interest of time, there's only so much I can present.
You just take your combinatorial design and set parameters and you'll get the cases.
There is no problem.
I mean, like,
No problem. The general one will keep much larger.
yeah.
Yeah, this is
What's the instruction for C4?
C4.
Yeah, it's like.
It's a
project-
projective plane.
Yeah.
Projective plane has no two lines intersecting.
So I do want to mention, even though I said I mostly wouldn't talk about hypergraphs in this talk, I do want to mention one interesting thing, which is that if F is an R uniform hypergraph, then if F is R partite, then this result shows that the extremal number is little o than to the R. So I'm just going to write this as the Turán density of F is equal to 0. Now, if F is not R-partite, then there's an interesting construction, or there's a very simple construction, which is you take R parts, and then you take every hyperedge that has one vertex in each part. So this is a blow up of a complete hypergraph on, this is just a complete R-partite, R uniform hypergraph. And this guy has density R factorial over R to the R. You can just compute it out explicitly. So that gives me a lower bound on my bound. And a general question is, when are there jumps in the set of possible Turán densities for some uniformity? So we can say that R factorial over R to the R is a jump because there aren't Turán densities below it converging to it. And in graph world, Erdős-Stone tells us that every Turán density is a jump except for one. But in hypergraph world, we know quantities that are jumps, we know quantities that are not jumps. Most quantities we don't know anything about. So I just wanted to mention this as another really interesting side effect of this hypergraph
One over
configuration.
R, so it's actually exponential.
Yeah, it's exponent.
Yeah,
1 over
sorry, E?
1 over
Yeah, 1 over e to the r.
approximately 1 over e to the
Oh, I see, yeah.
That's Sterling, yeah.
Oh, yeah, yeah. Not number of edges to the R.
E, yeah, exactly, E.
But you said a value is a jump if it's not a limit point. What?
Yeah, I think I was speaking very, very loosely, but the idea is that some possible Turán densities are limit points of other Turán densities.
But you have dense intervals or stuff like that.
Yeah, so it's known for, I think, 3 uniform hypergraphs, that if you take a family of 3 uniform hypergraphs that look like this, so you build a cycle with this sort of component and then have it wrap around. That family has Turán density, I'm going to get this wrong. I think Turán density approaching 1/2 from above, but not equal to 1/2. So 1/2 is not a jump by that definition. Maybe it's approaching from below.
Yeah, I wanted to ask, like, is it like well ordered even? Like, do we know anything about the structure?
No.
It's known to be not well ordered, or is just
We don't know anything. Yeah. I was trying to figure this out, and it's possible that we know it's not well ordered, but I was having trouble extracting these results. This is still something on my reading list. I believe, but I'm not 100% sure that there are examples that are both limit points from above or there are some examples that are limit points from above, and there are, I believe, some examples that are limit points from below. But yeah, there are points that we know to be limit points. There are points that we know to not be limit points. There are lots of points that we don't know anything about, I think, is the summary of what we know for what we don't know for hypergraphs. So let's finish the proof of Erdős-Stone. So the last idea in the proof is called supersaturation, which essentially says that if I have, this was essentially Hamlin's question, if I have a graph with density much more than the Turán density of F, then I can actually find a lot of copies of F. And I think this idea was due to Erdős, but I'm not sure exactly when, sometime in the 60s or 70s. So this is a for all epsilon greater than 0. There is delta, and there's delta greater than 0 and n sufficiently large. That any graph G with at least with edge density at least epsilon more than the Turán density of F has the number of copies of F is basically n to the number of vertices of F. N to the BFF copies of F.
This was discovered later in the paper of combinatorial property testing of which really started that area by Goldbach. It's the same.
Okay.
Yeah, I don't think they knew about it, but I guess, found the same book. If you pick a random subset set of vertices with the size of F, you'll find a copy of them.
Yeah.
With constant property. But properties.
Oh, I see.
Right? I mean, if you cannot remove a few edges to make it F3, then that's it.
Yeah, no, for me, the challenge is realizing that that's
knew
not
about
really tested.
properties.
Oh, and I should say if n is at least this big n, that depends on epsilon. So I think the proof of this is more computational than it is interesting. So instead of going through the proof in detail, I'll just say take n so that the extremal number of, sorry, this should be big N. Is at most pi of F plus epsilon over 2. So just pick n sufficiently large that once you've hit this big N, the Turán density is, or the extremal number is genuinely at least epsilon over 2 close to the Turán density. Then if you do the computations carefully and you choose a random n set, let's call it U in G, then the expected density of U is going to be pi of F plus epsilon, because the expected density of U is going to be the same as the expected density of G. Now, you can't have density at most pi of F plus epsilon 2 too much, or else the average density won't be pi of F plus epsilon. So because this guy has density at least this in expectation, the since that's it, this density is at least pi of F plus epsilon over 2 with some constant probability. And it's very easy to show with probability at least epsilon over 2. So I will do the computation.
So what's the relationship between capital N and the size of the number of vertices of it?
Little n is bigger than big N. That's the only thing.
That's the only thing. Then
Yeah.
density is not preserved. If you take small subgraphs, then
No, but the expected density of a small subgraph is the density of the big graph. So if I have a big graph and then I pick k vertices from it, and then I pick big N vertices from it, the expected density of the small subgraph I've picked is exactly the edge density of the original graph, because every pair of vertices is equally likely to be picked.
Well, the define density you normalize by the number of possible edges in the answer.
Yeah. So the density is right up here. Little e is the number of edges, and
You
little e
mean
is the
that
number of
because it's
vertices.
a constant fraction of the.
Yeah,
Yeah. The density of that.
yeah. Yes, so I know that a given edge is present in G with, or a given, if I pick a random pair of vertices, the probability they form an edge is this probability. So if I take a random n set, the probability that a pair of vertices in that random n set form an edge is also going to be at least this. And that means that this random n set has probability at least this slightly smaller quantity with some constant probability. And this means that with probability at least epsilon over 2, this random set contains a copy of F. So I can do out the rest of the computation if anyone wants to see it. That looks like a no. But if you then just compute out the number of copies of F using this observation, you conclude that the number of copies of F is beta then to the number of vertices. So in other words, if you pick V of F vertices, there is some small but constant probability that they form a copy of F. So that's really helpful because it means that we can use hypergraph Turán to help us. So one immediate corollary of supersaturation and hypergraph KST is that the Turán density of F is equal to the Turán density of any blowup of F. So I'm going to denote this as F adjoin. I'm going to use T because that's what I used in my notes, but this is a different T from KST. And what this means is if I have some graph F, here's my favorite graph. Then if I want to blow it up, if I want to take the T blow up of F, then I replace each vertex with a set of T vertices. And then I put complete bipartite graphs wherever at that edges. Actually, it just occurred to me that we will be happier if I call this thing S. So do that.
So this is just to say that kind of you can just put this inside the block for click.
Yes. Yeah. Yeah, if you take the blow up of a clique and then you take the relevant pairs of parts that are pulled out by F, that's another way to define it. So how do we prove this? So first, this graph is just bigger than that graph. So it's just harder to find this graph than that graph. So we have this inequality for free. This is just definitional. For the other side, suppose that there was an epsilon gap for some epsilon greater than 0. Then by supersaturation, any graph with so this tells me that there is some there is some graph G that's free of the blow up, which has this density. But that's a problem because we know that G has this many copies of F. That is, if I pick out V of F vertices at random, there is a constant probability that they will form a copy of F. So that means that if I build a V of F uniform hypergraph, by taking one copy of, I'm going to build this hypergraph with a bunch of different copies of V. And I'm going to put a hyperedge on 4 vertices. Let's call my hypergraph H. If and only if those same 4 vertices form a copy of F and G. So does the construction make sense? I'm building my hypergraph by taking one copy of V of G for each vertex of F. And then whenever I take one vertex from each part, and those vertices gave me a copy of F and G, I'm going to turn that into a hyperedge. So this hypergraph I built by this observation, this hypergraph is dense. It has edge density at least delta. And that means that if n is sufficiently large in terms of all of our other parameters, we're in trouble because hypergraph KST tells me that if my edge density is at least delta, if my edge density is theta of n to the number of vertices, or theta of n to the uniformity rather than little o of that, then it has a copy of KSSS. But now if I look at a copy of KSSS in H, what does it turn into in G? It turns into exactly a blow up of F. So that's a proof that the edge density of a blow-up of graph, the Turán density of a blow-up of a graph is the same as the Turán density of the original graph. This immediately gives that this immediately gives that the Turán density of a blow-up of KS Sorry, I apparently just completely confused my S's and my T's in my notes, and I apologize. So the Turán density of a T blow-up of KS plus 1 is going to be equal to the Turán density of just KS plus 1, which we know. And now for other graphs, suppose the chromatic number of F is S plus 1. Then I know that F is a subgraph of some S plus 1 partite complete graph. And this gives me definitionally that the Turán density of F is at most the Turán density of KS plus 1. Now, if we return to Erdős-Stone, that matches the lower bound that we had before. So I think that's roughly what I wanted to say in the first half.
So this proof is due to?
This proof is due to, I think, Erdős in 1971. I will say Erdős-Stone originally only proved this first thing. And then Erdős and Simonovitz observed that actually this thing is an easy corollary. So this theorem is sometimes cited as Erdős-Stone, sometimes cited as Erdős-Stone, Simonovitz. I think I've been scolded for citing it both ways before.
You really needed this only for cliques F.
Yeah. But I think later on I do want to use this for other graphs. I think in hypergraph world, we have this same result, but in hypergraph world, everything gets weirder, as we're going to see in the second half. So
Take 5 minutes.
yeah, I was going to say, let's take a 5-minute break. And so for the second half of the talk, like I said, I want to talk about, I think it's actually, I want to talk about hypergraphs. So the first half was more expository. I think the second half is going to be a research talk. So like I hinted, the Turán problem for hypergraphs is just very hard. And I think part of what makes it hard is that in a lot of cases, we don't even know what the right constructions are. We have absolutely nothing like Erdős-Stone, like no conjecture like Erdős-Stone. We don't even have a hint of it. So coming back to, I guess now I should put this in the title. Coming back to the definitions, all of the definitions are basically the same, except that the Turán density of an R uniform hypergraph is going to be divided out by n choose R. And a lot of the stuff we said is going to hold true. In particular, you have analogues of supersaturation. You have the result that we know exactly when Turán densities are 0 versus at least R factorial over R to the R. And it would be very natural to conjecture that, well, okay, at least maybe for cliques, we have some analog of Turán's theorem. And this is blatantly false. A conjecture of Turán from the 60s is that the Turán density of the tetrahedron, or 3, is equal to 5 nines. And Turán had a construction, but since then it has been shown that there are actually quite a wide variety of constructions that avoid the tetrahedron that have this particular density. So I'm not going to, yeah, I don't think I will, no, I do remember it. It's like this. You split your vertex set into 3 parts. And then you take every triple that lies in either 2 and 1 in that direction or all 3 parts. So that was Turán's original construction, but there's a whole host of them.
So the point is, I mean, the number is the correct one you would have conjectured,
Yeah.
but the fact is that it's not unique.
Yeah.
That's the surprise.
And I think the best upper bound we know is 0.55. It's off by like 1/100 at most. So there's a technique called flag algebras that essentially tries to encapsulate graph inequalities into semi-definite programming and sort of hammer out as much computational power as you can from graph inequalities and Cauchy-Schwarz type sum of squares inequalities. And so that technique has gotten 0.55 something. So there is absolutely no reason why this should not be true. We just don't know how to prove it. Another even simpler conjecture, this is due to Mabai in 2003, is that if you take if you take the tetrahedron and you take off an edge, so now this is the 3 uniform hypergraph with 3 vertices and 4 vertices and 3 edges, is 2 sums. And this one, there is seemingly there is only one construction that we know, which is you take a Steiner triple system. So you take, I think I can draw it. You take a graph on 6 vertices where every pair of it has the property that every pair of parts is in 2 types of edges with other parts. So I think this pair of parts is also in an edge that goes over here. So you take some Steiner triple system, and then the weird thing is that within each of these 6 parts, you put the same Steiner triple system. So you divide each of these 6 parts into 6 more parts, do the same thing, and you get a sort of fractal construction. So this thing looks kind of blow-up-y, kind of fractally, but the reason I'm bringing it up is that it's so simple and we had absolutely no idea how to do it. And we also have the upper bound up to probably 1/100. Flag algebras gets very
So
close.
what did Osborne, we proved Osborne had a theorem which was determined the constant of one of these using flag algebras. I thought it was the tetrahedron minus an edge. Or maybe it was either
So
or.
there's a result that says that if you avoid both K4 3 and you have no 4 vertices that induce exactly one edge, then this is tight.
Okay, yeah.
So I think that might be what you're
That's
thinking
what,
of.
yeah, that's what I was.
Yeah,
this
so
is the flag algebra.
There's a lot of results of this flavor. If you avoid the subgraph you want to avoid, and then some other thing, because we can't really prove the thing we want to, then you get some fiddly thing whose Turán density you understand. So there are several small examples that we do know the densities of. And not surprisingly, all of these look kind of blow-up-y. So if you, I think this was one of the first examples. This was due to Frankel and Farini in the 80s. There's one edge. Here's another edge, and here's the third. We know that this guy has Turán density exactly 2 nines, which is 3 factorial over 3 to the third. So the extremal construction is given by a complete 3-partite graph. And now you notice that I'm playing a little bit fast and loose. I put a number on the left side and a graph on the right side. But by this, I mean, this is the structural result for this forbidden graph. And I have no better way to notate that, so I'm sorry. Another of the, I think, really early results was for the phonoplane. So this is, you take 7 vertices, and then these are points in projective 3 space over F2, I think.
Yeah.
And you take as edges every line in that space. I'm not going to draw all of them, but so on. Or maybe I will draw all of them. And then there's one more. The Turán density of this thing, which is called the phonoplane, is known to be 3/4.
Projective like plane.
Yes. So this was due to Duquesne and Ferretti in 2000. And I think the last example I want to mention, because this is maybe the only thing I know that's kind of like an analog of Erdős-Stone, is you can build this thing called the extended clique. And what I do is I start with a clique on that many vertices. And then for each edge of the clique, I turn it into a hyperedge by adding some more vertices. So I'm turning this edge into a 5 uniform edge. And I'm turning the, and so on. So I've got a graph that like kind of looks like the clique, but it's not a complete R-partite. It's not a complete R-uniform graph. It's some sort of R-uniform extension of a 2 uniform clique. So it's known that the Turán density of this guy equals, or the structural result is that the extremal construction is a blow-up of a complete graph on one fewer vertex. So it's not a coincidence that all of these constructions look blow-uppy, because blow-ups are sort of the only thing we know how to prove things about. And later on, we're going to see some constructions that are a little bit more fractally, but still look blow-uppy. And I think one of the things that I would really like to understand is, how do we show Turán type results for graphs or for hypergraphs when the extremal constructions could be more varied or don't look like blowups or are not stable? So the family of hypergraphs I want to talk about today are called tight set. Yep.
I have a question about the stability.
Yeah.
You could still ask the stability question even if you have several extremal cases, right?
Yeah.
So it's independent of being actually unique.
Yes-ish. So I think maybe here's an example that I'd like to keep in mind. Take a tournament. And I want it to be regular. So it's on odd number of vertices. It's known that every such tournament has the same number of directed triangles. And so I can build this into a 3 uniform hypergraph G with each directed triangle turning into an edge of G. And I think there are some problems. This family of constructions all forbid some very nice families of graphs, and they're conjectured to be optimal for some of these families. So my question for you to think about is, what would a stability result look like here?
Everything that, I don't know, goes above the bound, like in the density sense. No, sorry. Everything that is close to the bound from below,
Yeah.
right? Like
Is close to one of these tournaments.
yeah.
Yeah, but how do you know which one?
No, I'm not saying that algorithmically, like I'm not saying algorithmically which one. I'm just saying this can still be a possible type of
Yeah,
result.
so it can be. I think this type of result turns out to not be strong enough to do the sorts of things you'd want to do with stability. Because with stability, you'd often like to say, well, okay, then we can clean it up and improve it towards the optimal construction. Whereas what you just said, one tournament looks stably close to another tournament, and we don't want that. So we want, if a graph is extremal, I want to say it looks like itself. It doesn't look, I don't want to say it looks like that other extremal graph.
I thought that this
No,
one was
that's not what I said. I didn't say that the perfect examples are close to each other. I said you have this metric space of edit distance between your object, and you have the class of good things, the optimal things. I'm just saying if you're like 1 minus epsilon in the local sense of the density, then you are delta of epsilon close to something in this optimal set. Like
so I think
we hope for something like that.
You can very much hope for things like that. I think, unfortunately, they turn out to be less useful when you don't have a unique or a few unique optimal constructions that you're sort of going in the direction of. And instead, you have just a much larger space of optimal constructions.
Well, I think what can happen.
So I think the answer is you can
family
do
of examples very natural structure, and this can be useful. But anyway, stability results can exist with many.
So the answer is you can have a stability result.
My question is actually the reverse. Like, do we know of any? We actually essentially don't know of anything that, like, you can approach the Turán bound asymptotically, but is actually in edit distance bounded away from any optimal construction, right? Like that is still open. So something which actually probably doesn't have this weaker stability type of.
I don't know of anything like that. It's possible that you could say that for technical reasons that's not possible.
Okay.
But let's talk about that offline. Yeah, it is a good question. So the class of hypergraphs I want to talk about today are called tight cycles. So this is some generalization of cycles. And maybe I will just start by drawing an example of a tight cycle for you in uniformity 3. So a tight cycle locally looks like this in uniformity 3, and then it wraps around and comes all the way back. So that's a picture, but what is this formally? So there's two parameters. There's the uniformity, which is just always going to be R. And there's the length L. Is you have vertex set V1 through VL, and you have edges VI plus 1, VI plus 2, all the way to VI plus L. Oh, sorry, VI plus R taken while. So in the picture that I drew, if this was vertex 1, this was vertex 2, vertex 3, 4, 5, and so on. And the last edge out here would be L1, 2. And I think I'm going to try really hard to avoid drawing paired cycles because I tried to do this in ticks and that also looked really bad. So my board schools have no hope. So there was a recent result, I guess recent as in 2023 now, so not so recent, of 3 authors. That determined the Turán density of these tight 3 and 4 cycles. So the exact quantity is some irrational number. I think it's 2 root 3 minus 3. I hope I got the irrational number right. But the relevant thing is that this irrational number comes from some fractally construction. So what is the construction? I take my vertex set and I divide it into 2 chunks. And I take every edge that has 2 vertices on the left and 1 vertex on the right. Now I'm going to divide this bit into 2 chunks and do the same thing. And then I'm going to keep iterating within the rectangle. So I get some fractally construction, and this, whatever this quadratic irrational is, it's the place where some cubic is maximized.
What's the ratio between the sides of the roughly?
It's something like 2/3 and 1/3, I think. 0.63 and 0.37. I think there's 2 things I should have stated when I stated this theorem. And that is, this holds for L sufficiently large and not divisible by 3. So this first constraint I want to talk about a lot more because there were some very nice ideas that went into getting it for sufficiently large L, as opposed to not knowing it for any L. The not divisible by 3 is quite simply because if L is a multiple of 3, or more generally, if L is a multiple of R, then this is an R-partite graph. And so its Turán density is 0. So you get genuinely different behavior for tight cycles of length 0 mod R versus tight cycles of other lengths mod R. And actually, as we'll see, for different residues mod R, you get different behaviors sometimes. So this was followed up by a result due to
that K43 minus an edge, it's not a tight cycle, or
it is a tight cycle. No, sorry, K43 is a tight cycle.
yeah. Oh, okay, but without
Yeah. Yeah. So for that reason, you could be pedantic and say, well, I guess I can only hope for this to be true for L at least 5. And actually, the flag algebras recently showed this for L at least 7. But flag algebra means computers, and it's not a human readable proof. So I think I want to talk a little bit about the human readable proof. And I also think that there's hope that this could extend to other families of cycles, which is the other reason I'm interested in it.
Also, this is equality for any large number.
Yes.
Not a limit.
Correct. So
Can you
then,
explain why this is extremal for this? I don't see it.
as in why it doesn't contain.
Why or why it's extremal? Why you cannot add anything? Or
Yeah. So this is, the first thing I will say is it's asymptotically extremal. So it is true that I could add theta and n squared edges to this construction and not create any tight cycle. But I only care about things in the theta and n cubed regime. As to why it doesn't contain any tight cycles, let's suppose that I had a tight cycle that contains this yellow edge. So maybe my tight cycle put vertex 1 here, and vertex 2 here, and vertex 3 there. Well, then vertex 4 would have to be in this oval, because the only edge that contains this vertex and that vertex must have its 3rd vertex in the oval. Similarly, the only edge containing 3 and 4 must have vertex 5 also in the oval. And the only edge containing 4 and 5 must have its 3rd edge in the rectangle. And so if you keep looping around, you realize that the only way you could start at 1, 2, 3 and eventually come back to 1, 2, 3 is if you took 0 mod 3 steps. So this does contain tight cycles of length 0 mod 3, but of course it does because it has density greater than 0. Did that answer the question?
okay.
Yeah, it is true that you can, this isn't the best possible graph for bidding specifically this one cycle, but it does turn out to be the best possible graph for getting a family, which I want to talk about in a sec. I think there's just one more result I want to mention that uses a lot of the same ideas. I think this is 2024. It came afterward. And so this is if you take a tight cycle and you subtract out one edge. So now you should think of yourself as, instead of taking the cycle and joining it back to itself at a pair of vertices, you take it and you join it back to itself at a single vertex because you've deleted one of the edges where you would have joined. For this guy, the extremal construction looks like this. So it's also a fractal. I take every edge that's in those three parts. And then within each part, I divide into three and do the same thing. And I keep iterating. And once again, this result has exactly the same conditions for L sufficiently large and not divisible by 3. And the last result I want to tell you about, which is mine, does the same thing for uniformity 4. And here the construction is really simple to draw. It's not a fractalizer at all. You take 2 chunks of vertices, and you take every edge that has 3 vertices in one part, and 1 vertex on the other part. And same conditions for L sufficiently large and not divisible by 4. So the thing I'd like to do is tell you a little bit about the ideas that go into all 3 of these proofs, why they're related, where this L sufficiently large is coming from. And hopefully, I think one of the nice ideas that was hinted at in these 2 proofs, and then this proof I think really was able to bring out, is this generalization of, well, we know what a graph that avoids all odd cycles is. It's bipartite. And all 3 of these results do some generalization of that to uniformity 3 or 4. And I want to tell you how to generalize that theorem to hypergraphs in all uniformities and to get some sort of nice coloring characterization, which maybe some of you will find useful for other problems, I don't know. And I also just think it's really nice in and of itself. So where is this?
So avoiding odd cycles means that there is a parity issue also.
Yes.
This original, so it comes.
Yes. So where is this sufficiently large coming from? I think right now I'm just going to talk about uniformity 3 since it's easier to talk about, and just think of everything as I'm saying, generalizing to all uniformities, including uniformity 2. So if you're familiar with that and you want to think about that, that's also cool. So where does this high long L come from? The first step in all of these proofs is to understand the Turán density of, instead of tight cycles, tight closed walks. And I'll tell you what those are in a sec. So what is a tight closed walk? A tight closed walk is like a tight cycle, but you're allowed to repeat vertices. So a tight closed walk is and I should say that walks are to paths in graphs as closed walks are to cycles in graphs, as tight closed walks are to tight cycles in hypergraphs. And if I ever say tight walk and tight path, I'm sure you can figure out what those are. So why is this the right thing to understand?
Analogue of further stone, then
Yeah,
there are most. You have many, and most of them will
Yeah.
be.
so let's say I had if I had many tight closed walks of length exactly equal to L, then I could do some sort of supersaturation argument. Or actually, I could just do hypergraph combinatorics Turán, just like we did before. So this sort of supersaturation argument would imply that I have a tight cycle of length L. Now, what if I had many tight closed walks of really short length? Well, there's actually a way to get around that. Tight closed walks of length, if I have a tight closed walk of length L minus R, I can extend it to a tight walk of length L by just tacking on the first R vertices a couple of times. So if I have a tight, sorry, both of these should be closed walks. If I had a closed walk of length L prime, which is say L minus 5R, then I could tack on 5 copies of X1 through XR and get a tight walk of length L prime plus 5R, which is exactly L. So somehow, if I had tight closed walks of length, if I understood what happened if I was avoiding tight closed walks of length up to L mod R, with that, sorry, up to L with that residue mod R, then I would be happy. But I've told you that I'm also allowed to forbid long tight walks. So the last step is, it turns out, and I'm not going to tell you how to do this, but it's not super challenging. I can delete a little o of 1 as L goes to infinity. This is something like L to the minus 1 over R. Actually, I'll just write it out. I can delete a small fraction of edges. And also delete every tight walk of length greater than L that can't be shortcutted. So what you might picture in graph world is you start with your graph and you delete a small fraction of vertices whose degrees are less than 1 over L. So then if every vertex in your graph has degree at least omega of 1 over L, then you can sort of shortcut any long cycle, because if you have a cycle of length much longer than L, each of these vertices has a neighborhood of size n over L. And so 2 of these neighborhoods will overlap in some vertex. And so I could shortcut the cycle like that. So the rough idea is
remainder mod R, right? Like this argument is robust to.
yes, so this argument is robust to that, and I don't want to do the details. But it is robust to that.
Edges, not really.
Yes.
Yeah.
Yes. So you should think of the argument morally as being this. Well, but really by delete the tuple, I mean delete the edges that contain that tuple.
So that's what you can delete, so that.
After you do this, the resulting graph has large degree in some sense, and you can use the large degree to shortcut. So if you combine all of these tricks, I'm speaking a little bit loosely here, but this first trick lets you turn short tight closed walks into longer tight closed walks. The second trick, although I really waved my hands, it lets you turn longer closed walks into, it lets you get rid of the longer closed walks that you can't turn into shorter closed walks. And if you combine all of these tricks, what you actually get for very little effort is that the Turán density of one of these tight cycles is equal to the, or is at most the Turán density of the whole family plus some additive error.
What's the difference?
Ah, sorry. Yes, I was not paying attention. Oh. And I'll just put the little o of 1. There. So this, you get this quantity up to some small additive error.
This is what you meant before that you moved to a family.
Yes. So now if you go back to the results I put, if you go back to the results that I probably erased, I told you that it was exactness, not some limiting. So how do you get rid of this error term? The answer is you understand this Turán density with stability. And however good your stability is here, that's how good the bound on sufficiently large L you get is. So the rough flavor of the argument is, suppose I have an extremal graph for this. I know it looks epsilon close to the extremal graph for this, where epsilon is this quantity, and I can make it as small as I want. Okay, now let me look at the edges that are there but shouldn't be there, and the edges that should be there but aren't there. And this type of argument is called a cleaning argument, where you bound the edges that are present in this graph, but not in this graph, and the edges that are present in this graph, but not in that graph. And you show that actually, well, this graph wins on number of edges because of its structure. So I really don't want to say much more than that, other than if you want to do a lot of work, you can use stability out here to get rid of the additive error term here. And it is hard. I think what I do want to say is I want to say something about how we understand the family of hypergraphs avoiding these tight closed walks, because I think that is something I can say in a short amount of time, and I think it's a really good result. So let's say I wanted to understand, I guess, a bipartite coloring of just an ordinary graph. Well, one thing I could do is I could take for any vertex, I could ask like, okay, if I have two vertices V and W, how can I get from V to W? Is there an even path? Is there an odd path? And recording the possible lengths of paths between V and W sort of captures all of the information you need for a bipartite graph. If there is an odd path between V and W, it means they're different colors. If there's an even path between V and W, it means they're the same colors. If they're both, it means that your graph is not colorable. So how does this work for three uniform hypergraphs? Well, what I want to do is I want to record something like I'm going to pick a three uniform edge, and I want to record the possible lengths of tight closed walks that start at V1, V2, V3 and end at V1, V2, V3. Only here's the thing, it matters that my tight closed walk end at V1, V2, V3 in the correct order, right? If it ends at something like this, then that's not a tight closed walk at all. It's some twisted tight closed walk that's weird, and we don't really know how to deal with this. So I want to write down this set. And I've called it TC for tight connectivity. And I'm going to define it as the, well, let me first try to define it and we'll see why this goes wrong. So let's try working with this definition and see what happens. Well, the issue is if I have something like this, it's possible for V1, V2, V3 to connect to permutations of itself by paths of arbitrary length. But the issue is sometimes I can then fit these together and get a tight cycle or a tight closed walk that starts here, goes through here, and ends here. So somehow I also want to capture information, not just about ways V1, V2, V3 can connect to itself, but also ways it can connect to all permutations of itself. And this is maybe a little bit heuristic, but let me just tell you what we're actually going to define this group to be. Or this set, I should say, since I haven't told you this group. I'm going to define it to be the set of permutations sigma. I'm going to define it as the set of permutations of V1, V2, V3, for which there is a walk to that permutation of length 0, mod 3. Why does this make sense? Suppose there's a walk from V1, V2, V3 to V1, V2, V3 of length 3, 4, 5. That's length 6, so let's go with length 7. Suppose we had this walk of length 1 mod 3. Well, I could extend it by just repeating V1 and then repeating V2. And now I have a walk of length 9 from V1, V2, V3 to V3, V1, V2. So in this example, 3, 1, 2 would be in this TC group, or TC set. It turns out to be a group. And to show you that it's a group, well, actually first, are there any questions about this definition? Other than it's strange, why would you do that?
So the last step you did is just cyclic shift, right?
Yes, exactly. So you can always do this type of cyclic shift to make a walk of some other length into a walk of length 0, mod 3. So that's why it's okay to only look at what's going on of length 0, mod 3. So here's an equivalent definition of TC. I'm going to say one ordered edge is tightly connected to another if there is a sequence that starts with V1, V2, V3, and then changes one of these vertices. Maybe we'll change V2. Then maybe, I don't know, change V1. So if there is a sequence of edges that changes one vertex at each time, preserves the ordering, and at the end of the day, you get to W1, W2, W3.
So in the third row, you might have V2 prime, right?
Yes, I did, sorry. That's a good catch. And it turns out that this group TC can be equivalently defined as the set of sigma in S3, where V1 V2, V3 is tightly connected to sigma V1, V2, V3. So in one direction, this isn't super hard to see. If there's a tight walk of length R, then that's the same as saying I can go from V1, V2, V3 to V4, V2, V3, V4, V5, V3, and V4, V5, V6. So if there's a tight walk of length 3 between these two edges, then they are tightly connected by the definition that I just covered. To see the opposite direction is not that much harder, but in the interest of time, I won't do it. But the important thing is, from this definition, it's pretty immediate that this TC is a group. Because if V1, V2, V3 is connected to sigma V1, V2, V3, then sigma V1, V2, V3 is connected to sigma squared of V1, V2, V3, and so on. So you have the identity, you have composition, and you have inverses basically for free.
That's more interesting when R is bigger.
Yes, So it's always some subgroup of the symmetric group, and when R equals 2, there's like only one interesting subgroup of the symmetric, maybe none, depending on how you count. When R equals 3, there's only 2 proper subgroups of the symmetric group. And when R equals 4, you can still list them. Like I can list them right now if I wanted to. But it gets more and more complicated as the symmetric group size goes up. And the reason this is useful is that this TC group exactly tracks the presence of tight closed blocks. So we can observe that the TC group contains a cycle 1, 2, 3, if and only if G has a tight closed block. Of length 1, 1, 3. And actually, if you stare at this, you realize that TC contains 1, 2, 3, if and only if it contains 1, 2, 3 squared, because it's a group. And that's equivalent to G containing a tight closed block of length 2, mod 3. So I'll leave it as an exercise that these are in fact equivalent conditions, and you can see this on the graph side too. So this is pretty useful. We now have an algebraic object that records the thing that I want to record, which is tight closed blocks of a given length. And I should say in general, I'll replace this by sig to the k if G has a tight closed block of length k modulo r. So when we're going in R uniform and modulo k, presence of kth powers, cyclic shifts, is what we use. So that's pretty useful, but it doesn't get us close to a coloring characterization. So what I want to do is I want to try coloring the edges of my hypergraph by their tight connectivity groups and see if I can profit. So let's just use this slide. I want to color each edge of G to represent its tight connectivity group. And so what does that mean? If the tight connectivity group of V1, V2, V3 is, actually I'm going to draw it like this, is maybe I'm allowed to interchange 2 and 3, but not do anything with 1. Then I'm going to pick some coloring of this edge that's symmetrized by the tight connectivity group. So maybe I'll color like the top half of my edge red and the bottom half of my edge yellow. I just want some coloring that's preserved under flipping, but not preserved under any of the other permutations. And if I were to get stabilized by the cycle, but not by any transpositions, I might do a coloring that looks something like this. So again, stabilized by rotations, but not by reflections. And why is this a reasonable thing to do? Well, if I have 2 edges that agree on all but one vertex, so they overlap on R-1 vertices, then this left edge is tightly connected to the right edge in the appropriate orientation. So if you stare at the algebraic property, what you realize is that actually you can take the colorings to be the same. So if this first edge was colored like this, then you can assume that the second edge was colored by reflecting it. So I'm not going to prove that because I am running a little bit low on time. But I do want to say that that comes from the definition of tight connectivity, definition 2. So what do you get? You get that every 3-uniform hypergraph has this type of coloring. And if we're free of tight closed walks of length 1 or 2 mod 3, then the coloring doesn't use this type of picture. So in fact, the coloring only uses this picture and a picture that looks like this to represent the identity. But I've drawn it kind of suggestively because I can always just replace this picture with that picture. So the result that you get is that a 3-uniform hypergraph avoids tight closed walks of length 1 or 2 modulo 3. If and only if you can color the edges with that picture, so that whenever 2 edges agree on all but 1 vertex, the coloring gets reflected. And you can derive a similar result in higher uniformity too, which is, can I have the projector?
Yeah. So this is really the analog of in a bipartite graph.
Exactly.
Even part or odd part.
Yeah. So if R equals 2, what you get is that you have only 1 coloring, and it looks like, I guess, red on the halfway, and white on the other half. Or maybe I can draw it even more suggestively like that. And the property you get is that a graph is bipartite. Sorry, a graph has no odd cycles, if and only if you can color the edges with this picture, i.e. direct them. So that if I have 2 edges that overlap at a vertex, then the coloring is reflected. So if they overlap at a red vertex, the coloring is reflected like that. And if they overlap at a white vertex, the coloring is reflected like that. So this is saying that a graph avoids all odd cycles if and only if you can direct the edges so that every vertex is either a source or a sink. And I can't draw these pictures very well, but this is the result I just showed for 3-uniform hypergraphs. And it's also worth mentioning that because you have this property that what's going on the edges is only determined by a given pair of vertices. Like a given pair of vertices determines the color of any triple containing it. You can actually pull this down to a coloring on pairs instead of triples. So that's how you get condition number 4 out here is equivalent to the rest of these.
So does it mean that you have the same greedy algorithm to determine the absence of tight cycles as you do in graph?
Yes.
Yeah, it's really greedy, right? You color this and you reflect.
Exactly the same thing works.
Then there's no coloring, so it's that content and otherwise.
Yeah, exactly the same thing works. The only difference is in graphs, you can turn odd closed walks into odd cycles, and you can't turn tight closed walks into smaller tight cycles. And then I guess for 4-uniform hypergraphs, the results are dependent based on the value of k modulo r. So if k is 2 modulo r, then you want to color with this particular tetrahedron, which is my best drawing of something that's stabilized by permuting the bottom 3 vertices and not the top. And again, that's the same as coloring triples of vertices by these 2 pictures, so that every edge is colored by these pictures in a way that fits. And this is the construction I showed you earlier. This is how you would color it if you wanted to use this theorem to show that it's free of tight cycles of 2 mod 4. And then for 1 and 3 mod 4, it just gets more complicated. And I think in general, if you have particularly composite uniformities, you're going to get particularly vast arrays of colorings. Though my hope is that only the ones that look like one symmetric group cross another symmetric group, like this first one.
But you have the same theorem for any R.
Yeah. So same theorem for any R. The challenge is computing what the, so if R is equal to a prime, then you know that only these colorings where you're only allowed, like the first two colorings, the first is S3 cross S1, the second is S2 cross S2. When R equals to P, that's the only type of coloring you need to worry about. But when R is composite, you can get all sorts of weird things, like this weird alternating group thing. But yeah, that's the theorem. And then if you want to then understand the Turán density, there are more hard steps, like what's the densest way to put these triangles described in condition 3 into n vertices. So that's what I have. Thank you. Yeah.
Great questions.
So maybe you mentioned this before, but like in the examples you gave, the density like pi was either rational, or there was one example which was irrational, but it had like only square root. So what about other irrationals or transcendental numbers?
We don't know if it's possible to get transcendentals. We don't. My guess is you could construct other irrational numbers if you really wanted to, by coming up with one of these fractally constructions, and then come up with a fractal construction that gives that irrational number, and then find something for which that fractal construction is extremal. And I think you probably can do this. I believe it is known that you can do this if you're willing to forbid finite families rather than single graphs. But it's completely open whether transcendentals are possible. Yeah.
How do you analyze the extremal number of this oriented coloring?
With pain and suffering. The way I did it is I picked a vertex, and I wonder if I have more slides. Nope. I picked a vertex and I colored its link using 5 colors corresponding to the 5 pictures. I picked a link that was better than average, meaning that I think the vertex was in, I think a vertex that was more likely to be the red point than the blue point of one of these triangles. And then I did a lot of Kruskal-Katana type and Cauchy-Schwarz type inequalities and found where they were all maximized.
Oh, and it happens to be the extremal.
Yeah, I would say I knew what the extremal construction should be. And then I threw everything I could, graphed every inequality I could on Desmos, and found a minimum of 6 inequalities that gave me the thing that I wanted.
And it's the same for the other 2 works?
No, so for the other 2 works, finding the extremal construction was much easier. I think in 3 uniform, you can do it using a symmetrization argument if you're familiar with that. But you still have to do work, but it's less messy by a lot. Like the ideas are very straightforward.
Yeah, I guess.
It's hard to set it, but here the right one is 8-4.
Yes.
Okay.
All right, thanks.